As a last example from section 14.6, let me show you how you can use triple integrals to calculate a volume. The formula that we need is that the volume of a solid Q is equal to the triple integral over Q of 1 dV, where dV is going to be dx, dy, dz in any of those 6 possible orders. The problem I'd like us to look at is problem number 21 from the text, which asks us to find the volume of the solid in the first octant bounded by the two surfaces z equals 4 minus x squared and y equals 4 minus x squared. So let's see if we can sketch the region first and then set up the bounds. Z equals 4 minus x squared is going to be a generalized cylinder. Remember, we get a generalized cylinder if one of the variables is missing in the equation, and we have no y in this equation. Now, if I sketch z equals 4 minus x squared in the xz plane, this is going to be a downward turn parabola. So it'll also come back and intersect the negative x-axis. But since I'm working in the first octant, I only need to draw the piece over here where x is positive. Now, since the y doesn't appear in this equation, then I'm going to take this parabola and I'm going to translate it parallel to the y-axis. So let's just come over parallel to the y-axis. And I guess something that looks more or less like that. So if I were to draw the entire cylinder, it'd be a downward turn parabola moved along parallel to the y-axis. So it would look something like this. So I'm just taking the front half of this. Now I know that I'm also bounded by the xz plane because I've got to stay in the first octant. But this shape, this cylinder, goes out forever along the y-axis. So if I'm going to have finite volume, there's got to be something which is capping it over on this side. And that's going to be this surface. Let's see if we can sketch the surface y equals 4 minus x squared. Now y equals 4 minus x squared is also going to be a cylinder. This time, it's going to be parallel to or moving along the z-axis. So let me begin by drawing y equals 4 minus x squared in the xy plane, and then I'm going to translate that up the z-axis. By the way, I just want to make a quick note that this cylinder had a z-intercept of 4 and x-intercepts of 2 and negative 2. So this happens to be 2 along the x-axis. Okay, now let's draw this parabola. This parabola is going to have a vertex over at 4 on the y-axis, and it has x-intercepts of 2 and negative 2. So this parabola is going to go out this way in the xy plane, and then it's going to continue back and intersect again at x equals negative 2. And then I have to take that and translate it parallel to the z-axis. So this point is going to go directly up and meet that curve. And as I slice, it's going to be as if I take a knife and take a vertical slice of this solid along this curve. So that's going to go up something like that. And I'm going to be removing this part of the blue solid, which lies on the outside of that parabolic cylinder. So this is what the region looks like. This back area is actually a square. Over here on the left and on the bottom, I have 2 flat sides, which are each roughly triangles. 2 sides are straight lines, and the third side is going to be a parabola. And then I have 2 curved edges. This is a vertical curved wall whose base lies along a parabola. And this is a roof kind of coming down the side, which is also in the shape of a parabola if you look at it down the positive y-axis. So this is going to be the solid that we want to set up the bounds for. Now, I say that students often like putting dz on the inside, and so do I. And I think that that would be great to set up the bounds setting z on the inside. Let me label my surfaces, and then we'll do that. This surface over here is y equals 4 minus x squared. And this top surface is z equals 4 minus x squared. And now I can erase a little bit. So to calculate volume, I integrate 1. I'll put the z on the outside, and I'll hold off deciding which order I want to put the x and the y. So for z, if I send a segment up from below, then I'm going to enter on the xy plane, which is z equals 0. And I'm going to exit on this curved roof, which is z equals 4 minus x squared. Now to set up the bounds for x and y, let's project into the xy plane. Now in the xy plane, I get a parabola which crosses the y-axis at 4 and the x-axis at 2. And I have this region here. This edge is part of this parabola, y equals 4 minus x squared. And notice that it'll be easier to write this curve in the form y equals than x equals. In fact, it's already written in the form y equals. So that suggests that we want to slice next parallel to the y-axis. And then I'll be entering on y equals 0 and exiting on y equals 4 minus x squared. So we're going to do y next, going from y equals 0 to y equals 4 minus x squared. And then the outer bounds are with respect to x, and x goes from 0 to 2. Now all we've done is set up the bounds. What you should do next is actually carry out the integral and find out what the volume is. And since this is an odd problem, you can check your answer using CalcChat.